Okay, I want to talk about quiz 5, the quiz we had on heat exchangers. This is on an evaporator. Now, an evaporator is the heat exchanger that's used in an evaporator, I should say, is used in a refrigeration process where you're trying to cool the air. In this case, you're trying to cool air. So I'm going to draw my heat exchanger as a little black box, and then I'm going to put in the air coming in. And the air is the hot stream, so I'll draw the air in red. The air coming in at 90 degrees Fahrenheit. And we're trying to cool it down to 50 degrees Fahrenheit. So to do that, we'll take heat out of it, and we'll call that Q. Internally in this heat exchanger, we'll call that Q, the heat going from the air into our refrigerant. So I'll draw the refrigerant in blue, have it come in countercurrent to the air, and this will come in with the quality I believe we gave of X equals 0.4, 40% vapor, and the temperature was 35 degrees Fahrenheit. Now you can see that since this is 35 degrees Fahrenheit and the lowest temperature of your air is 50 degrees Fahrenheit, that the heat's going to flow from the hot stream into the cold stream. So let's draw this cold stream coming across in the evaporator. Now the heat exchanger is going to operate pretty close to constant pressure. We're going to make that assumption here that the pressure doesn't change. So as long as it's evaporating, as long as it's saturated, if the pressure doesn't change, then the temperature won't change. So the temperature coming out will be also 35 degrees. But now X equals 1. So what we need to, we'll call this state 1. We'll call this state 2. Call the air coming in state 3. And the air coming out state 4. Now, all we need to do to find Q is an energy balance. Now this is R134A. So the enthalpy here at state 1, H1, is equal to 1 minus X, 1 minus 0.4, times HF, the enthalpy of the liquid, which is 23.3, plus 0.4, the quality, times Hg, which is 108.1. Switch back to yellow so you can see it better. H1 comes out to, let's see, H1 comes out to 57.2. That's BTUs per pound mass. Now coming out at state 2, H is equal to Hg, so H2 is equal to 108.1. So it's fairly straightforward to find Q now. We'll do an energy balance, and I'm going to draw in green the, let's say, call it the subsystem or the system I'm doing my energy balance on. So I'll draw an energy balance about this part here, and we'll have the energy in, which is m dot of the refrigerant, H1, plus Q. Q is coming into the system the way we've drawn it, plus Q is equal to m dot of the refrigerant times H2. Or Q is equal to m dot of the refrigerant times H2 minus H1. It's gaining heat, so H2 will be greater than H1. And this will be 10 times 108.1 minus 57.2, and this comes out to approximately 509 BTUs per minute. By the way, there's another unit, especially when we're talking about refrigeration, another unit of heat transfer that we call a ton of refrigeration or a ton of cooling. A ton is equal to 200 BTUs per minute. You may have heard this about your air conditioning units. A ton is equal to 200 BTUs per minute. So what we have here in this evaporator is about, see, 509 in tons. Divide that by 200. We have about a 2.5 ton unit. So that's kind of a handy number to keep in mind, because you'll hear that a lot when you're talking about air conditioning or heating. Tons of heat flow. Okay, now the next part of the problem is to find what the mass flow of the air is. We have air coming in here, and we want to know its mass flow. Let's call it m dot sub air. And we know it goes from 90 degrees and cools down to 50 degrees. So as you recall, the H for air, or the delta H for air, at low pressures we'll treat it as an ideal gas, so delta H will be Cp delta T. So I can write, let's see, we called this 3, called this state 4, and we can do now a balance on this subsystem here. Make this our subsystem. And we have m dot air H3 in is equal to Q out plus m dot air H4. Or, if we solve for m dot air is equal to Q divided by H, let's see, 3 minus H4. And if we substitute Cp delta T for delta H of the air, we have Q divided by Cp times T3 minus T4, which is a drop of 40 degrees Fahrenheit. So Q over Cp delta T would be mass flow of the air. So m dot of the air is equal to 509 BTUs per minute divided by Cp, which for air is 0.24 at these conditions, at these temperatures, approximately 0.24 BTUs per pound per degree Fahrenheit, and multiply that times 50 in the denominator, and that comes up to mass flow of the air of 5.3 pound mass per minute. So very straightforward. You just change the area that you do your balance on to find, it's the same Q going out of the air and into the refrigerant, and that'll get you your mass flow of the air. Last thing we need to do is find the diameter. Let's draw it in blue. The diameter of this pipe leaving with the refrigerant in it. We want to know the diameter of that pipe. And so we can find that the volume, the specific volume of the refrigerant at that point is Vg, which is equal to 1.047, and that's feet cubed per pound. So the volume flow rate is equal to the mass flow rate times the specific volume, which is also equal to the cross-sectional area of the pipe, a cross-section, times the velocity. And we want to limit this velocity to 6 feet per second. So what we'll do is substitute in here V dot equals m dot, which we know is 10 pounds per minute. Well, let's get that into pounds per second, because our velocity is in pounds per second, so we'll divide by 60 seconds per minute times the specific volume, 1.047, is equal to the cross-sectional area of the pipe, which is pi d squared over 4, times the velocity, which is 6 feet per second. Now, I'd encourage you to pause and check and make sure your units are all good there. If you solve that for d, algebraically you come up with d equals 0.19 feet, which is approximately 2.3 inches, 12 inches per foot, so that comes out to 2.3 inches. Now your pipes come in regular diameters, so you need to buy a pipe somewhat larger, just the next size pipe up, in order to keep the velocity from getting higher than 6 feet per second, and that was your criteria. Limit the velocity to no more than 6 feet per second, so you need a slightly larger pipe than that, and the next size up in this instance was 2.5 inches, which would be the solution to part C. So that takes care of quiz 5. Now this is, again, I want to stress that this is an evaporator. This is a heat exchanger, which is commonly used in refrigeration, and I have one of these in the closet where my air conditioner sits. You probably have one in your car. It sits under your dashboard. There's a little heat exchanger there where air is blown across. Air is blown across the coils that have Freon in it. So let me draw that. I guess the air in blue going across this Freon. I'm sorry, the air is in, let's make the air in red because the air is the hot stream, flowing across this coil of Freon that comes through and exchanges its energy with the air. So very common system. Be able to do these calculations all around this thing.